Carbon to chlorophyll ratio for ICM is a value supplied by the modeler. Okay, so you need to have some sense. You either have a sense of what it is, and those of us who've been around for a while do. You can also, if you're lucky enough to have particulate organic carbon and chlorophyll data, you can try to derive it from field data. There's a lot of, I won't go into that, but you know, if you have some data, you can try to derive it. Okay, so that takes care of light. Now, what about nutrients? Remember that the two things that determine algal growth rate are light and nutrients. And here we are. This is what Jim was talking about a moment or two ago, a Monod equation, or also called Michaelis-Menten. And you know, it looks a lot like that production versus irradiance curve. The shape in general is that. What it says is, on this axis we have, well, we'll look at the equation for a minute. This should be pretty standard or familiar to everybody. The parameter that determines the impact of nutrient limitation, if you will, is this thing KH. And that's the nutrient concentration at which the maximum growth rate is halved. That's why it's called KH. And once again, so you could see if the D in this case is the nutrient concentration, if KH equals D, then this function is exactly 0.5. If the of nutrients D is much, much greater than KH, Fn approaches 1, which is to say there's no nutrient limitation. If D is much, much less than KH, then Fn diminishes, and that's what's shown on this curve. This is the nutrient divided by that half saturation. When the nutrient is greatly in excess of the half saturation, the nutrient limitation effectively comes up to 1, or there is no nutrient limitation. When the nutrient concentration is very small compared to the half saturation, then growth starts diminishing, becomes limited, nutrient limited. We have to combine, well, the other one is temperature. I think that'll be the next zap. Okay, so we use, this case, we use a, algae have an optimum temperature for production, and we allow it to actually decrease when the when the optimum temperature is exceeded. Growth will actually go down. Okay. Now, sometimes what we'll do is we'll parameterize this such that when it actually kind of levels off rather than goes down, and by manipulating model parameters you can do that. So, but basically speaking, it's shaped like this, and actually the shape that does that is a probability curve. This is what the temperature function looks like. So when the temperature is above or below the optimum, it's this. I wouldn't worry too much about the exact, you know, where that came from or whatever, but let me say it gives us the shape that we want, which is it smoothly approaches a maximum and declines on the other side. So now we have temperature, nutrients, and light. And we need to combine these to get a growth rate, or if you will, a specific production rate at those conditions of temperature, light, and nutrients. And we do this in steps. How did we devise these steps? Trial and error, keeping in mind that we had a goal which was to reproduce primary production measurements that had been observed in the bay. So the first thing we do, what we do is actually that we figure out what the maximum production rate would be given the temperature and the nutrients. So we take the we take the physiological maximum production rate, and we take into account temperature and nutrients. So we reduce the physiological maximum by temperature and nutrients. Now what we've got is a maximum at ambient temperature and nutrient condition. And then what we do is we construct that, P versus I curve. So effectively what we do is every model time step, we say, what are this temperature, what's the nutrients? What's the maximum growth rate that is possible for that temperature, those nutrients, and then we say, now what about light? Okay, so then we reduce it according to light. So that's what we do. Every model time step, we create a P versus I curve. Then we have the light, or we have the irradiance, and away we go. Couple of other things while we're at it, but this is now we're going to start talking a little bit more about ICM for a minute. But your model input variable is Einsteins per day. It's the total photosynthetically active radiation experienced over the daylight hours. And what we'll do is we're going to take that total and we're going to fit a sine wave to it for the day length. So this actually, computes it, basically says the sun comes up and about noontime it gets light and sunset it goes down. So you give it the total Einsteins, you give it the day length, and these are model input variables, and we're going to talk a little bit about what we call the meteorological files later. But if you do that, this is inside the model code. That will compute the instantaneous irradiance, Einstein per meter square per day, from the total Einsteins in that day. So that basically is how we take the physiological parameters that are reported by algal scientists, particularly the maximum production rate, how we take the nutrient limitation, how we take the temperature, and how we combine that to get an algal growth rate.
So the Einsteins per day accounts for met conditions like clouds and stuff like that. So that's all in the time series. That's all in the time series.
It's all in the inputs, yeah. Okay, so where do we stand here?
Okay.
I don't know if that's worth.
Got it.
Okay, let's go to the next one. I'll mention, I don't have a graph to accompany this. We account for two kinds of respiration in algae. Basal metabolism and photorespiration. Okay, basal metabolism, in this case, what we call BM, is necessary to maintain life, if you will. It's respiration. It's the energetic cost for algae to exist, if you will. And it's dependent on temperature, but basically it's a constant. Photorespiration is the energetic cost of photosynthesis. Okay, so basically what photorespiration is it's a function, it's a fraction of the growth. If I computed the gross carbon fixation, there's an energetic cost of fixing that carbon. So the respiration is a fraction of the growth. It's the energetic cost of fixing the carbon, plus it's the basal metabolism. So in the dark, there's no photorespiration because there's no growth, but there's metabolism. During the light, there's the basal metabolism plus the energetic cost of fixing the carbon. So it's a fraction of the growth rate.
Any reason you didn't just take that that growth rate BRES and put it in the
Excuse me?
growth rate directly? Just reduce the growth rate?
You could do that, but why don't we do that? It gets hairy because take the growth rate and recall that the growth rate is based on the photosynthetic, the specific, and the specific photosynthesis that's reported doesn't
take account of that. Okay.
So I'm trying my damnedest to stick to just what those
guys do.
Picky scientists impose on us. Okay. So another thing I don't have a graph for, but it's worth looking at. Recall that we had. Let's go back up for a minute. So we have this predation term. And you notice for a minute that the predation term, it's not, in this representation, it's not multiplied by the algal biomass. A very typical algal model would put PR inside here, so its predation is some fraction of the biomass. So we don't. Okay, why not? Or how do we handle predation? This is actually we'll try to be formal about it here. So predation in the water column, if you think about it, is, imagine for a minute that it's a filtration rate by zooplankton. It's the algal biomass and the biomass of the zooplankton. Okay, so this is sort of abstract, but it's the predation. Predation is a filtration rate, the algal biomass, and the zooplankton biomass. And if you check, okay, so, but we don't model zooplankton anymore. And how do we know what the zooplankton biomass is? Well, we don't really. But what we can say is that the zooplankton biomass, on the average, is some fraction of the algal biomass, right? If you have, probably, we're just going to say offhand, the biomass of the predators, the biomass of the zooplankton is some function of the algal biomass. So if we do that, what we come down to, so the zooplankton biomass is some fraction of the algal biomass. The predation, the key is that it comes down to be proportional to the algal biomass squared. And since you don't really know the zooplankton filtration rate and you don't know this proportionality, you combine them and you come out to predation is some function of algal biomass squared. Okay? It turns out, empirically speaking, this is a rationalization for something I discovered by accident. But this is really a key to getting algal biomass and primary production right. Okay? What'll happen is if you have the predation linearly proportional to the algal biomass, the system gets unstable very quickly. And what this really does, I'm just giving you the voice of experience. I'm not going to show you that. Trust the voice of experience. What this one will do, though, is that as the algal biomass is very small, if you square a small number, you get an even smaller number. So the predation is very low on very small algal biomasses. But when the algal biomass starts going out the ceiling, this is a square, so the predation gets very high, okay? So but it's not, like I said, it's not linearly proportional to the algae, it's a square. And I'm just going to say again, experience shows that this gives you a nice, stable behavior. And that's just my experience, but then you can actually go through this process of saying, well, why should it be quadratic? And you find out that you can justify what you're doing through some simple, like I said, relating the predator biomass to the phytoplankton, that sort of thing. So now we've got the predation taken care of. Okay, well, more stuff. Okay, so algae are quantified as carbon. Okay, so many, well, they're carbon. So many gram carbon per cubic meter, that's our algal biomass. Now, algae are not only made of carbon, among their other constituents are nitrogen and phosphorus. And in our model, we do very careful accountings of nitrogen and phosphorus. So how do we account for the phosphorus that's bound up in the algae? And what we do is, this expression, if you will, is an expression for total phosphorus represented in the model. And the key here is that B is algal biomass. This is carbon. And we have this, here it's APC. This is the phosphorus to carbon ratio of the phytoplankton. So what we're saying is that the total phosphorus, we'll go backwards, is the particulate inorganic phosphorus, the refractory particulate organic, or this is the inert particulate organic, the refractory, the labile, the dissolved phosphorus, and the phosphorus that's bound up in the algae. And APC is a parameter that you as a modeler will specify. And there are classic Redfield ratios, for the composition of algae. You can go with a Redfield ratio. They get stretched, particularly for phosphorus, the factor of 2 or something like that. But effectively, you as a modeler are going to specify the phosphorus to carbon ratio. Let's go down. Similarly, we have a nitrogen to carbon ratio. So implicit in the, implicit in the expression for total nitrogen is the nitrogen content of the phytoplankton. And well, I don't know if we get into this a bit or not, but when, remember I told you when algae die, they don't go to heaven, they go to dissolved organic carbon. When the algae die, you have to account for that internal nitrogen content. Okay, so you not only have to root the algal biomass to the various carbon state variables, but you have to root this algal nitrogen to various nitrogen state variables. And the rooting, if you will, is highly empirical. And when you calibrate a model, one of the things you'll calibrate is exactly where you put that algal nitrogen and that algal phosphorus. But you do, your mass balance requires you to keep track of that. And it's in, the model code will do that, but there's a lot of parameter specification that you're going to have to indulge in, okay, we'll let that go for now. Enough said.